Welcome back. This week we're going to look at buoyancy and stability of floating bodies. Now you might wonder why that's important. So I'd suggest that you go and take a look just at the outset at a clip such as this one here, showing vessels in storms on the ocean. And I think you'd agree that it's vital that these vessels are stable and that they don't tip over and cause untold damage and loss. So have a look at that, and then we'll proceed and look at the principles of buoyancy. So let's start by looking at why something floats in the first place, and we need to understand Archimedes' principle for that. Now, Archimedes' principle says that the upthrust on a body immersed in a fluid is equal to the weight of the displaced fluid. Now, that body can be immersed partially or completely in the fluid, it doesn't matter. The point is, for that to happen, it must displace some fluid. Now, the word displace means to push something else out of the way. So when you place a body in a fluid such that you displace some of that fluid, then you will get a corresponding upward force. Okay, we call that the upthrust. This upthrust acts through the center of gravity of the displaced fluid. So if this here is our vessel, our ship floating in the ocean, there's the surface of the ocean. The fluid that had to get out of the way for the vessel to be where it is, in other words be displaced, would be this portion of fluid here. Obviously that cross-sectional area that I'm showing there multiplied by the length of the vessel would give you the volume that's been displaced. Now that volume of seawater would have had a center of gravity at its midpoint. And that point would have been here, because here is your displaced fluid. Its center of gravity would have been there. This is of course assuming that the ship's sides are vertical and the bottom is vertical. It's a slightly simplified explanation, but nevertheless this would have been the center of gravity of the displaced fluid. So that is the point through which the upthrust acts. So that force that we achieve by displacing liquid acts through point B, and it would be straight upwards. Next, let's talk about G, the center of gravity of the body. Now in this sketch over here, it is a very simplistic situation where we have, for example, a rectangular block of wood that is floating in water. Its center of gravity would be at its center point of the shape. But please understand that that would not be the case in a ship, for example, where the center of gravity would be at a different point depending how the ship is loaded. So this G at the midpoint of the shape is purely for homogeneous bodies like a block of wood, a block of polystyrene, etc. But B, that is not negotiable. That is at the center of gravity of, remember, the displaced liquid. Now when it comes to stability, we need to understand this concept of metacenter. Okay, now metacenter is the point at which the line of action of the upthrust cuts the original vertical through the center of gravity. Okay, so the easiest way to understand that is, let's pretend that this is a yacht, and let's pretend that there's a mast sticking up here. That would be the original vertical through the center of gravity. Now when this vessel is displaced in roll, in other words it leans over a little bit clockwise, a little bit anti-clockwise, that original vertical is rotated slightly. Now if you take the upthrust, which remember acts through B, and you take a line vertically upwards, where that line of action cuts that original vertical is this new very important point called metacenter. And with that concept comes metacentric height, which we're going to use shortly, but let's get the definition out of the way now. Metacentric height, this is the distance from the center of gravity of the floating body to the metacenter, and we'll refer to that as GM. In other words, the linear distance from point G, which is the center of gravity of the vessel, to point M, which is that definition we just did moments ago. Right, for the next section, which is to do with stability, we need to recall what I was. Now earlier in the syllabus we studied second moment of area of a certain shape. Now we're going to need that here. And in fact what we're going to need is I of the surface of flotation, the cross-section at the surface of flotation. So if you can picture a yacht, which I've attempted to draw over here, and if you can picture the waterline, that is where the water would cut the vessel, and you were to draw that in 2 dimensions, you would get a cross-sectional shape, which I've hatched over here, of more or less that. That would be the shape of the 2-dimensional shape of the waterline. Now you need to find the second moment of area of that shape, which clearly in this case would be fairly complicated, but if it was a rectangular shape, it would be a lot easier. Do you remember BD cubed over 12? Now how you use this is, there's this little formula which says B, the distance from B to M. Now remember what B was, center of buoyancy, which was after all the center of gravity of the displaced fluid. The distance from that point to the metacenter you can calculate by taking I, which we've just discussed, the second moment of area of the surface of flotation, divided by the displaced volume. Also, what's important to note here is the bigger this distance, the more stable the vessel is. And finally, we look at I in various planes depending which axis of stability we are looking at. If you are looking at roll stability, now remember that is the vessel rolling from left to right about the axis XX. If that is the stability you are calculating, then you would use I about axis XX. If on the other hand you are looking at the pitch stability, which would be the ability of the vessel to resist pitching, which is nose up, nose down, then you would use I about YY. And in each case, the bigger that number, the more stable the vessel is around that axis. In other words, the more reluctant it is to be displaced from its neutral position. Now, in all shipping instances, we would want this situation here, where M is above G and the vessel is said to be stable. What stable means is if it is displaced by something, for example a wave or wind or cargo moved across the deck or whatever, it naturally wants to right itself. It wants to go back to its original position. Here these images have all been drawn showing some degree of displacement from the neutral position, but when M is above G, you will see that the upthrust acts through the original vertical, reaches point M up here like we discussed, and that would then cause what's known as a righting moment, an anti-clockwise moment, which would try and get the vessel back to where it belongs, back to level. If on the other hand we were to use this instance, a rectangular shape on edge, we would clearly find that it is unstable, and the reason for that is M is below G. And lastly, if we were to put something perfectly round in the water, like a log, a tree stump, a tree log rather, you would find that it's completely neutral, meaning that wherever you displace the two, it would simply stay there. So if M coincides with G, the object is neutral in terms of stability. If M is below G, it is unstable. Any displacement will accentuate and continue until the object falls over. And if M is above G, then you have a stable situation, which is the normal situation that you want. Now, one final matter that we need to sort out before we can continue is that of overturning and righting moments. So here we have a vessel that is stable, and something has tried to overturn it, and that something, it could be displaced cargo, it could be an external force pressing down on it, whatever. That something is holding it in this slightly, let's call it skew position, and it is stable. And when something is then stable, we have equilibrium obviously, which means that whatever overturning moment is present is equal to a righting moment that is trying to bring it back to where it should be. Now that righting moment is, after all, the upthrust, which we said acts through point B, wherever that might be, multiplied by some sort of moment arm. Right, now that moment arm, if you analyze this triangle over here, and this triangle has in it distance GM, and it has angle theta, which is the amount of roll that we have, the amount of displacement from the original position. We would have sine theta equals x over GM, making x distance gm sine theta. So we can take that x and we can put it in over here, and we end up with vessel's weight times distance gm times sine theta. But now if this angle is small, which hopefully it would be for a large vessel, let's assume it's a small angle, maybe 2 or 3 degrees, something like that, you will find that sine of a small number like 2 or 3 or 4 degrees is very, very close to that number in radians. So we can simplify the formula further. For small angles, we can say overturning moment is equal to weight of vessel times distance gm times theta, but measured in radians. So in practical terms, what that means to us is, if we know the weight of a vessel, and if we know its metacentric height, we can quickly work out what angle of roll or pitch we're going to get with a certain overturning moment. So if that was a big container ship, and you were the captain and you needed to know how much the ship is going to lean over or roll, if I go and put a certain portion of the cargo off center, I could say the overturning moment is the weight of the cargo multiplied by the distance to where the cargo is from the center line, and we could quickly make a calculation to find how much roll we're going to maintain with that displaced cargo, as long as we know the weight of the vessel, which you would normally know, and of course the metacentric height, which is a vital value to know for your vessel. Now remember, to work out these numbers, you are going to have to deal with a second moment of area, this story over here. And to make that easier, here is a quick reference of common shapes, which you might or might not already have. And we might be able to use some of these common shapes in the shapes of vessel we're going to deal with. Rectangle, triangle, circle, etc. Remember, here's the I values. So these are the examples we're going to be doing from this text over here, this prescribed text, and we're going to be doing those numbers over there. So let's start with a very simple buoyancy calculation, nothing to do with stability yet. What they say here in number 1, a rectangular pontoon, which would just be a floating rectangular shape. They give you the dimensions, and they tell you it has a draft of 1.5 meters. Now in nautical terms, that means the portion that is sticking into the water, that's the draft, 1.5 meters. And the water that it's floating in is fresh water with a density of 1,000 kilograms per cubic meter. Firstly, you must find the mass of the pontoon. Now Archimedes' principle says that the weight of water displaced is equal to the weight of the object. So how much water is displaced? Well, 12 by 5.4 by 1.5 is how much water you have to get out of the way to make this thing float. And it would have a weight of this much. Now mass is weight over g, so we can find the mass of this object must be 97,200 kilograms for it to lie 1.5 meters in the water. Now amazingly, if you were to move this pontoon from fresh water to seawater, for example, if it was floating in a river mouth and you towed it out to sea, where the water density had changed to 1025, that of seawater, you would find that the vessel or the barge would now float at only 1.46 meters draft, and that is because of the changed density of the water. So look at that calculation and see that you get 1.46 meters draft. A few terms that you must get used to. Sometimes with ships and boats, etc., they talk of displacement, and that's just from the whole Archimedes principle. If they talk of a vessel with a displacement of 10,000 tons, it means that the vessel must be 10,000 tons in mass, because it displaces 10,000 tons of water. Anyway, in this case, they say the area of the water line is 1840 square meters, and it's not necessarily rectangular, it might be this shape here. It is moved to a seawater dock, and after removal of cargo, its displacement is reduced to 8,500 tons. They took off some cargo and it rose up slightly in the water. Assuming the sides of the vessel are vertical near the waterline, that's important, so that the area of the waterline doesn't change as it rises and falls for the sake of this problem. Assuming that the sides of the vessel are vertical, we've done that, and taking the density of fresh water as 1,000 kilograms per cubic meter and that of seawater as that much, calculate the alteration in draft. So originally it lay at a draft of 5.435 meters. That was taking into account the fresh water and the original displacement or mass of the ship. Then things changed and the displacement changed, as did the density. So you just simply did a fresh calculation and you found that it was now lying at 4.507, and the question asked for the change, delta x. So the difference between the two numbers was 0.928 meters. Now number 3 involves the age-old debate of why ice floats in water with a portion of the ice sticking out of the water, and also what happens when that very same ice melts, becomes water, and the question of whether the level of the water would rise or not. You could experiment with a glass and an ice cube floating in it and measure the level of the water before and after the ice has melted. And amazingly, you're going to see that there is no change in height. And to understand that fully, you've got to understand the principle of buoyancy. So let's start with the cubic meter of ice in this case with specific gravity 0.9. Remember what that means. The specific gravity is an indication of how dense the ice is. It is only 0.9 that of water when it is frozen. So it is less dense than water. Anyway, that makes it float freely on the water surface. Firstly, you must find how much of the ice is exposed. So let's see how much is sticking out, how much is exposed over here. Right, the mass of the ice block must be 900 kilograms because it is a cubic meter, and that we are told that it is 0.9 that of water, the density. So it means it must be 900 kilograms. Had it been normal water, it would have been 1,000, but it's not, it's 900 because of the specific gravity being 0.9. Now, according to Archimedes' Principle, it means that 900 kilograms of water must be displaced to make this ice block float. Now, water of 900 kilograms would have a volume of 0.9 cubic meters. So it follows that this portion under the water must have a volume of 0.9 cubic meters. Now, if it is a meter by some distance, what is that some distance if it is all to come out to a product of 0.9 cubic meters? So the portion underwater is a meter by a meter by a certain distance into the water, and that must total 0.9 cubic meters. So it follows that x must be 0.9 meters. So the portion sticking into the water must be 0.9 meters. So if 0.9 of the 1 meter is underwater, it follows that 0.1 meters must be sticking out of the surface of the water. So that answers question A. Now when the ice melts and becomes water, it shrinks basically. So the 0.9 cubic meters that used to be submerged will now go down to 0.81 cubic meters using the ratio of 900 to 1,000. And then there was a piece that was sticking out previously, and it was 0.1 cubic meters, and it too will shrink to 0.09 cubic meters. Now if you add the 0.81 to 0.09, you will get to 0.9 cubic meters. And remember that that was what was displaced in the first place, so there would be no change in the level of the surface of the water. The 0.9 cubic meters fits precisely in the 0.9 cubic meters that was originally displaced. So amazingly, when ice melts and becomes water, there is no change in the surface level of the water. Now in number 4, we look at a very common device that we're all familiar with, and that is the ball valve in a toilet cistern. And the way this works is you have a buoyant sphere attached to the end of an arm, and that arm is attached to another shorter arm, and that presses on a piston which acts against the mains water supply, which, as we know, can be anything up to 5 bar in pressure, quite a lot of pressure. So that pressure from the mains supply, the water supply in your house or your building, acts on a piston, and obviously there's some force from right to left, and that is counteracted in perfect equilibrium with the upthrust from this buoyant sphere on the end of the arm. And if you get the ratio just right, then you can achieve perfect balance and you can block off this water supply. If the level of water in the cistern drops, this ball drops and it allows this piston to move off its seats and allows a little bit of water in and refills the cistern. And as we know, the automatic process continues and the ball rises until it blocks off the system again and you maintain a water level in the cistern. In this case, we've got to find what the pressure is in the main supply, and they tell us that a quarter of the ball is submerged. So what we have in a more simple drawing is the force due to the pressure on the piston. Now remember that pressure is force over area, so force is pressure times area. So whatever that pressure is multiplied by that area would give us the force acting on this arm from right to left. And then in equilibrium we would have the upthrust multiplied by that distance, and we would have clockwise moments equal to anti-clockwise moments if this is to be in equilibrium. First of all, what is the volume of a sphere? Well, 4 over 3 pi r cubed is the formula for volume of a sphere, and a quarter of that would be 0.4418 times 10 to the minus 3 cubic meters. Next, we take moments about the pivot, that's this point over here. Clockwise moments equal to anti-clockwise moments. And we remember that upthrust is equal to the weight of the displaced liquid. So the displaced liquid, we've worked out a short while ago, that is its volume times density will give us the mass of the displaced liquid, times 9.81 gives us the weight of the displaced liquid. Multiply all of that by the moment arm, which is 0.25 meters, and we would have our clockwise moment, all of this here, and that is equal to the anti-clockwise moment caused by the mains pressure multiplied by the area of the piston, because after all, force is pressure times area. So pressure times the area. Remember, it's a circular shape with 10 millimeter diameter, so pi over 4 d squared, and you've got to multiply by the 0.025, which is the moment arm. And we solve for the pressure, so the pressure must be 551.83 kilopascals of mains pressure to hold all of this in equilibrium with a quarter of the ball submerged. This one you can try yourself. It's exactly the same question with a few variables changed, and they simply ask you to find what fraction of the ball will be immersed. So you can have a look at that yourself and then have a look at the solution if you need to. Number 6 is basically a revision of number 2, so I'm going to leave you to do that one as well. It's just to do with draft, and we've handled that in number 2. So work through it yourself, and once you're happy, have a look at the solution again as if you need to. And the same applies to 7 and 8, simple displacement draft calculations. In number 9, we look at our first stability problem, and there's some odd wording here. They talk of ship's boats, but that simply means a tank. So this ship, which happens to have a 13,000 metric ton displacement, has a tank, 2 tanks in fact, and one of the tanks is filled with 60 metric tons of water. But because it's on one side of the vessel heels by 2 degrees 16 minutes. So it rolls over slightly by 2 degrees 16 minutes. And we're told that this tank is 9 meters from the center line of the ship. So basically what it means is 60 metric tons at 9 meters from the center line causes that much roll. We've got to find the metacentric height. So we have an overturning moment caused by that water off center, so it was 60 metric tons, remember to multiply it by 9.81, times the 9 meters moment. So that would be the overturning moment. The righting moment, we said, was weight, metacentric height, times angle of roll. So there's the weight of the vessel, its mass times 9.81, times the thing we desire, which is the metacentric height, times the angle of roll in radians. Now 2.267 degrees is the amount of roll. Remember to multiply that by pi over 180 to get the angle in radians, and you're going to find the 1.048 meters of metacentric height. Also remember that 2 degrees and 16 minutes is 2 degrees and 16 over 60 degrees. That's how we got to the 2.267, because 16 minutes means 16 sixtieths of a degree. And number 10 is very much the same. Vessel displacement 1500 metric tons, and a weight of 16 tons is moved 8.25 meters across the deck. So you shift it maybe from centerline to a position 8.25 meters from the centerline, and you find that you get some roll. That roll is measured with a pendulum which had 175 millimeters of movement at its lower end, the pendulum being 1.5 meters long. So from that you can obviously find the angle. Let's start with that. That pendulum with its 175 millimeters of displacement, 1.5 meters long, would indicate 6.7 degrees of roll. So once again, overturning moment equal to righting moment for that equilibrium condition. The 16 tons times its moment arm is equal to the weight of the vessel times the metacentric height times that angle you just worked out. So the metacentric height is 0.754 meters. So the practical use of this is, if the ship's captain did not know the metacentric height, he could use a pendulum or other device to measure angle of roll, and he could move a known portion of cargo a known distance across the deck, and from the calculation find the metacentric height for his ship, which would indicate how it was loaded. Now this rather alarming YouTube clip you might want to go and look at, and that will show the danger of too small a metacentric height, or possibly an unstable metacenter position, resulting in a bit of a catastrophe. So have a look at that one. So in number 11 we have a pontoon of 90 metric tons floating in seawater. We are given the dimensions, and we've got to find the metacentric height. We know this density of seawater. And then finally they tell us that the center of gravity of the pontoon may be taken as its geometrical center, which would indicate that this pontoon was made all out of one homogeneous material. So maybe wood, polystyrene, something lighter than water that floats on water, but its center of gravity will be at the center of its shape. So if you were to draw a line corner to corner, you would go through the center of gravity. First thing is to find out how much volume of liquid is displaced using Archimedes Principle. 90 metric tons in seawater means that that much volume must be displaced. And given the other two dimensions of length and width, we can find the draft. There must be 0.9756 meters sticking into the water for equilibrium. Now the waterline shape is a rectangle, and if we are interested in stability about the longitudinal axis xx, we need to find Ixx, which is b d cubed over 12, b d cubed over 12, in other words Ixx, which we find to be 421.87 meters to the fourth. And armed with that, we can use the bm equals I over v formula, knowing I, we've just worked it out, and knowing V, we worked it out earlier, and we can immediately find that the distance from point B, the center of buoyancy, to the metacenter is 4.804 meters. Now that is not the metacentric height. The metacentric height is the distance from G to M. So we've got to still pinpoint a few dimensions here. Firstly, B, remember that is the center of gravity of the displaced liquid, must be at half x. So half of x would take us to, or would give us this dimension, which is half of x. Now remember that the vessel is 3 meters deep, so the distance from its center of gravity to the lower face of the vessel must be 1.5 meters. Now if we subtract from that 1.5 meters this distance, we will get B to G. So we do that down here. 1.5 meters minus what we just said leaves us with 1.048 0.0122 meters from B to G. Now remember, M is somewhere up here for stability, and G to M, which is what we desire, which is the distance from here to here, is the distance from B to M, which we already know, minus the little piece we just worked out. So GM is BM minus BG, and there's our final answer at 3.8 meters. Now number 13, I want you to try yourselves, but let's just explain something in the question which might not be completely clear. It gives you the vessel's length, width, and displacement. It's floating in seawater, that's all fine. When a mass of 20 metric tons is moved 6.75 meters across the deck, the vessel inclines 5 degrees. So that's an overturning moment, no problem there. Now here's the issue. The second moment of area of the water plane, remember that's what we need for our I value, about its fore-aft axis, in other words the longitudinal axis, is, and here it is, 65% of the second moment of area of the circumscribing rectangle. So what that means is, if that's your vessel's waterline shape, they are saying that its I value is 65% of what it would have been had it been rectangular. Okay, so you're going to use that to find the I value that you need. So stop the video here and make a good attempt at this before looking at the solution. In number 14, we've got a rectangular pontoon once again, and we have the dimensions and the mass, and then we're told that on the deck is this heavy boiler that's been attached, and we also have its mass. And then they also tell us that the centers of gravity of the boiler and the pontoon may be assumed to be at their centers of figure. What that means is the center of gravity of the pontoon can be taken to be at its middle point there, and likewise the pontoon itself will have its center of gravity where these two lines cross. Okay, so from that we can find the center of gravity of the combination. And to do that, I've taken the total mass times the distance from a reference edge, which in this case I'm using the lower face, to the new center, or the actual combined center of gravity. I'm making that distance bar y, and then the mass of each times the center of the distance to each one's center of gravity. So the combination has a center of gravity at 2.7 meters from the lower face. So that is the center of gravity of the combination. Then from Archimedes' Principle, it follows that 117 cubic meters of water must be displaced if we have that much mass of vessel. In other words, if the displacement of the vessel is that much mass. Okay, so next is to find the draft, and because this is a vertical sided, very simplistic rectangular pontoon, we can work out that the draft would be distance x multiplied by 10.5, which is the length, times the width, equals the volume displaced. So 1.547 meters is the draft of the vessel, how much it sticks into the water. The center of buoyancy would be at half that height, so the distance from the lower face to the center of buoyancy would be z, which is simply half of x, because we remember the center of buoyancy is at the center of gravity of the displaced liquid. The displaced liquid is this portion. Half of that height would take you to point B. So immediately, using simple arithmetic off the dimensions, we can find the distance from B to G. We can also find the distance from B to M from the I over V formula. Remember what this is? Second moment of area of the two-dimensional shape at the water plane over the displaced volume. So the distance from B to M is 2.79, and the distance from G to M is BM minus BG. Remember, we've done that before. So GM is, after all, what we're looking for, the metacentric height at 0.864 meters. And this up to here was for rolling, because we were taking I about the axis, the longitudinal axis, which would be the axis about which roll occurs. We are also asked to look at it for pitching. And for pitching, you simply take this sketch over here and you turn the axis, rather than being longitudinal axis, you go through an axis about which pitching occurs. So the I would be B d cubed over 12, B d cubed over 12, still over the same displaced volume, and you would find that the metacentric height for the pitching axis is in fact 4 meters. So by seeing that this is bigger, this metacentric height is 4 meters and the other one is only 0.864, it would suggest the vessel is more stable in pitch than in roll, which would make sense for a vessel shaped like this. Okay, number 16 is very similar to the previous one, except that working out the second moment of area is slightly more complicated because they tell us the barge has 2 semicircular ends. So you can try this one, but let's just give you some tips. When you're working out IXX, you're going to be using B d cubed over 12 for the rectangle, and you're going to have to add to that the second moment of area of a circular shape. I for a circle, pi d4 over 64. I for a semicircle, pi d4 over 128. You can use either. So I about longitudinal axis xx would be I for the rectangle, plus I for one full circle, assuming that we've got the semicircle and another semicircle, both about the same axis. So you could either go twice that for a semicircle or once that for a full circle, and you get 6.93 meters to the fourth. I'm going to leave you to work out the rest because it's exactly the same as before until you get to the metacentric height of 0.201, and then finally there's a little bit of a question about overturning moment and righting moment, and we've done that before, so you can have a look at that and you find the 5.71 degrees.